Okay, so today, this is more of gases and chemical reactions. It's kind of like a continuation of the first video, mainly because I only had a few problems in there and I really wanted to make sure you guys understood this. So, anyways, gases and chemical reactions. Something important that you need to know, because this is going to come into play later. I'm going to give you this conversion factor. 1 mole of gas is equal to 22.4 liters. That's like the standard conversion factor for gas. Okay, so now that we got that out of the way, this will help you if you have like a stoichiometry problem that doesn't necessarily fit into doing the ideal gas law or one of the other gas laws. You're still able to figure out a volume just because of this value right here. If you go back to the other ones and you just multiply the moles that you calculated by, or the moles that you had by this value, you could get the same answer. Anyways, but sometimes we don't have all the information and we need to calculate it based on the ideal gas law. So, all right, let us do this problem. So I'm going to write down the chemical equation or whatever a little bigger. So this is going to produce hydrogen gas because it's metal reacting with an acid. And then some ionic compound that's aqueous. All right, so let's calculate this. We have a 1 gram sample of zinc. And it's added to a dilute solution of hydrochloric acid. It dissolves to produce hydrogen gas according to this equation. So the resulting gas is collected in a water-filled bottle at a temperature of 30 degrees Celsius, and P is equal to 760, which we know is equal to 1 atmosphere. Perfect. So now we just have to use this information and some stoichiometry to get to our final answer. So let's figure this out. I don't know zincs off the top of my head. Let me pull up the periodic table. It's right here. So zinc is 65.38. So zinc equals 65.38 grams over moles. All right, so we have 1.00 grams of zinc times 1 mole over 65.38 grams. So let's do this in the calculator just so we get an exact answer. So you're going to have about 0.0153 moles of zinc. So these are the moles of zinc we have. We have to go from moles of zinc to moles of hydrogen. So let's do that. 0.0153 moles of zinc. And then, let me make sure I wrote that down right. Yeah. Times 1 mole H2 over 1 mole of zinc. So that means you have 0.0153 moles of hydrogen that is created in this reaction. So we have to convert the temperature. So the temperature equals 30 degrees Celsius. You had 273 kelvins. You're at 303 kelvins. So here's our temperature. And our pressure is 1 atmosphere, so let's figure this out. So PV equals nRT. we have the moles, the temperature, and the pressure, and we're trying to figure out the volume. So we divide P out, divide P. So V equals, we have 0.0153 moles times 0.0821 liters times atmospheres over moles times Kelvin times 303 kelvins divided by 1 atmosphere. So let's plug this in and see what we get. So 0.0153 times 0.0821 times 303. And then that gives us about, where is that? 0.380 liters. So that's how you would figure this one out. So the question was, what volume does the gas occupy? So let's make sure we label that. Okay, so I'm going to give you a second to copy that. Alright, let's move on. So, sulfuric acid, the industrial chemical produced in greatest quantity, almost 45 million tons per year in the United States alone, is prepared by the combustion of sulfur in air to give sulfur dioxide, followed by the reaction of sulfur dioxide with oxygen in the presence of a catalyst to give SO3, which reacts with water to give sulfuric acid. The equation below is how it is made. Sorry, I had to drink some water. Interestingly, this right here happens at coal plants, or it used to happen a lot more frequently because they didn't have a lot of the pollutant filters on their smokestacks at coal plants. So a lot of sulfur dioxide would get out into the atmosphere and react with oxygen, which would create this, which would react with water vapor and give you sulfuric acid. So you'd have acid rain, and that's how that would, happen. And even though it wouldn't lower the pH, I mean, it did lower it quite a bit. It was like 4 or 5 pH, and normal soil's a little higher than that. It's still 100 times, lower than it would be if it didn't have the acid rain, 100 to 1,000. And even though that's still not like a super, super strong concentration, or super strong acidic pH, it was enough to defoliate trees and pretty much acidify the ground, so nothing was growing there. As soon as they started cleaning up the amount that they did, it's still very dirty, but it eliminated a lot of the acid rain problems. Alright, so a little history lesson there. Let's figure this out. So, what volume in oxygen at 22 degrees? So, volume of O2. Let me rewrite the equation. Sorry, I got on a tangent there. 2S solid plus 3O2 AQ plus 2H2O, and then that's liquid, is equal to 2H2SO4 AQ. Okay, so anyways, what volume in liters of O2 at 22 degrees Celsius, so 22 degrees Celsius, and a pressure of 745 millimeters of mercury, is required to produce 1 ton, or this many kilograms, of sulfuric acid? Alright, so let's break this down. we need to make 907.18 kilograms of H2SO4. So 1 mole of H2SO4 is equal to 232.64. So you have 64 plus 32.06 plus 2. So that's going to give you 98. Yeah. 98.06 grams per mole. So we have a lot to do. First, let's convert this to grams, and then we'll convert it back to, we could just convert it to kilograms. So 907.18 kilograms. And then we have 98.06 grams per mole times 1 kilogram divided by 1,000 grams equals 0.098 kilograms. 0.09806 kilograms per mole. Alright, so this is the molar mass in kilograms. So first let's figure out how much oxygen is needed. So we have to figure out how many moles we have in here to make this amount. So 907.18 kilograms times 1 mole over 0.09806 kilograms. So this is going to be a very large number. So 907.18 907.18 divided by 0.09806. So this is going to be 9,251 moles. So 0.27 moles. It's a lot of H2SO4. So now we have to work backwards to figure out how many moles of oxygen we need. So 9,251.27 mole H2SO4 times, where's the reaction? 3 moles of O2 divided by 2 moles of H2SO4. And then I'll go back and show you that's where the reaction came from. 3 and 2. Alright, so let's cancel. We cancel these moles, and we're in moles of oxygen now. So let's do this in the calculator. Times 3 divided by 2. So you're going to end up with 13,876.91 moles of O2. Alright, so this is how many moles of O2 that we need to make 1 ton of sulfuric acid. So what volume do we need? Alright, PV equals nRT. So divide the pressure out. So you have V equals 13,876.91 mole times 0.0821 liters times atmospheres over moles times Kelvin times, and I forget what the temperature was, 22 degrees Celsius. I never converted that, my bad. So just so you know, you just add 273 to it. So that's going to be 295 times 295 kelvins divided by 1 atmosphere. So I'll put that right here. 22 degrees Celsius plus 273, 295 kelvins. Alright. So let's do this one. Was it 1 atmosphere? Oh no, it wasn't 1 atmosphere. Sorry. I'm making all sorts of mistakes. Here, what I'm gonna do is I'm gonna copy this. Move it down a little bit. So you have 745 millimeters mercury, 760 millimeters mercury, and that cancels to give you atmospheres. 0.9802 atmospheres. We'll just do that. So divided by 0.9802 ATM. And then this one is going to get moved down just a tad. Actually, let me just insert another page. Alright, and I'm going to move some of this stuff down. Move this part down. Alright, so temperature, pressure, and then we have everything we need. So let's plug this into the calculator. So we have 13,876.91 moles times 0.082821 times 295 kelvins divided by 0.9802 atmospheres. So the volume in liters is 342,880.86 liters. And that would be your final answer for that, which on an industrial scale seems like, on a regular scale that seems excessive. But industrially, that's, how it's normally done, is you have huge amounts of this gas being made at any given time. Alright. So we have one more problem to do. Alright, so... I'm sorry if these are a little back and forth. I don't really solve any of these before doing the notes, so might be a little, not so smooth at first, but we'll always end up at the right answer. Alright, how many moles of nitric acid can be prepared using 450 liters of NO2 at a pressure of 3372 torr and a temperature of 22 degrees Celsius? Alright, so how many moles of nitric acid? Nitric acid is HNO3. It's a super, super strong acid. Really nasty stuff. It's used industrially a lot to make many different things. How many moles of nitric acid can be prepared using 450 liters of NO2? Which, right here. So this is a stoichiometric relationship. And then... many moles of nitric acid, blah, 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 blah. Oh, so this one we're going to have to do backwards. So remember, we have all the information we need to figure out how many moles of NO2 that we have. So we're going to have to do this twice. All right, so let's do pressure first. 3372 torr times 1 atmosphere over 760 torr. So let me clear this. We have 3372 divided by 760. So that's going to give you 4.44 atmospheres. Alright, so we have our pressure. So let's label that P. And then now we need our temperature. We have 22 degrees Celsius equals, we'll just add 273 to it. That's going to be 295 kelvins. So now we have T. And then we need, do we have pressure? We have volume. Volume, we don't have to convert it, it's just 450 liters of NO2. So let's figure out how many moles of NO2 we have using this formula. So we're going to divide out RT, and then N equals PV over RT. So N equals PV over RT. So let's plug that in. And then let's do it all the same. Alright, so we have 4.44 atmospheres times 450 liters divided by 295 kelvins times 0.0821 liters times atmospheres over moles times kelvins. So whatever you don't have is the unit you're going to be in. Oops, we are looking for moles. So you're going to have moles because that's what we're looking for. So let's plug this in the calculator. 4.44 times 450. Close the parentheses and open a new set after you divide. You have 295 times 0.0821. And then that's going to give you 82.5 moles. So we have 82.5 moles of NO2. So we have to figure out how many moles of nitric acid can be prepared using that many moles of NO2. So this is when you do your stoichiometry. 82.5 moles times, and we go back to the equation, it is 2 moles of HNO3 divided by 3 moles NO2. So let me move this out. So this cancels and this cancels. You essentially are multiplying this by 2/3. So you have 82.5 times 2 divided by 3. And then that's going to be 55 moles of nitric acid. So technically this would be the answer, but what if I added another condition on there? What if I wanted to know how many liters? So how many liters of nitric acid are made? Well, that's very simple. You just plug everything else back in. You have the moles, you have the temperature right here, and you have the pressure. So PV equals nRT. So you would divide out the P, and then you have V equals nRT over P. So you have V equals 55 moles HNO3, 0.0821 liters times atmospheres over moles times Kelvin. And then that's multiplied by the temperature, which is 295 kelvins. And I don't remember what the pressure was because I keep forgetting. And then that's divided by 4.44 atmospheres. So let's cancel everything. That's canceling, and that's canceling. So we're left with liters. So you have 55 times 0.0821 times 295 divided by 4.44. So that's going to get you 300 liters. So you have volume equals 300 liters of nitric acid. So that's how you can use that equation to go back and forth. I mean, pretty much it. So if you have any questions on how to use stoichiometry to do this, please use my office hours or email me and I'll try to answer it. But right now for gases and chemical reactions, we're done. I've done about 6 examples. The rest is up to you. There's practice problems for you to do. And if you have any questions, please ask.